Topic today, Hess's Law. Now Hess's Law is kind of complicated, so we're going to look at a couple different examples. Now Hess's Law is important because in chemistry you want to determine how much it's going to cost you or how much energy you're going to produce if you're going to do a reaction. Now cost you would be endothermic, so you're going to have to pay the electric bill, and that's going to be associated with, you want to predict what you're going to spend before you spend it, because you might not have enough money and then you go bankrupt. Now the other problem would be if it's exothermic, you don't want the reaction to get too hot and cause an explosion or melt some of your equipment, damage your equipment. There are two issues there you have to really be concerned about: what it's going to cost and if it's safe. So Hess's Law, we're going to watch a couple of videos. I want you to take some notes on that from the videos, and then we'll try to explain it again from the textbook. Yeah, I'll check those tomorrow. It's like a homework, classwork. The back side will look at homework, and the front side will call that together.
Our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's Law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary, as long as we change the delta H associated with it in the appropriate way.
A mouthful. It's much easier to explain if you actually do it. So let's actually go over here, and let's say I have this reaction. Sulfur plus oxygen gas yields me sulfur trioxide, and I have no idea what the delta H is. Okay. My delta H is now going to be, what is it, negative 594 kilojoules. Okay. Okay. And because I flipped it, this going this forward direction is going to be an endothermic reaction, but if I reverse it, it's going to be becoming an exothermic reaction. So this is going to be negative. So my delta H is going to be negative 198.
When you're solving for these types of equations, this is the equation you've been given. The tricky part is finding these two equations. And because you can get distracted by the coefficients out front, you're thinking, oh, okay, there's a 2 there. There's not a 2 there. But just be aware that if you have the right element, it's going to work out. And then she finds the SO3 there, SO3 here as well. So this is the tricky part. It is not easy finding because you have to go into the book and find the equations. They're just not like listed for you. They are listed in a table, but they're not going to be listed by like the ones you need. At the top, that is. She divided everything by 2, and she did get that 3 halves for the coefficient up there. We're not really concerned about that. We're really more concerned about the product being 1 mole, and you can use that in your reactions to determine how much energy you're going to be giving off. If you have, if you're doing a conversion factor and you have 10 or 15 moles, that's really the goal up there, is when you do your conversion factors for 1 mole. Very common with the CO2. It's trying to make. So if you're trying to make HF, you're going to want to get that, because your product's what you're going to sell and make money. You tend to have to order the reactants to figure out how much it's going to cost you, right? But you want to do the most effective reaction, because there's more than one way to make coffee. There's this guy over in like Japan who he makes it by hand. He doesn't have like the $1,000 coffee machines. Concept, right. But yeah, you can do this more than one way. A lot of different reactions. Horse in the Kentucky Derby. Secretariat. And when was that? You know what year that was?
1996.
Try 73. 1973. Do you know the distance that they run at the Kentucky Derby?
A mile.
1.5 miles.
Wait, but it says 1 out of 4 at the very top of the screen.
It's 1.5 miles. It's 1.5 miles. Now, what was the time that Secretariat did?
I know it was 45 lengths ahead of the horse and stayed
1 minute and 59 seconds. He did 1.5 miles in 1 minute 59 seconds. So, does anybody know the average speed, Jake? What would be the average speed of Secretariat? What was the average speed of Secretariat? Because, I mean, you have the distance she traveled and you have the time she traveled. the average speed, because when she comes out of the gate, right?
36 miles an hour. 22 miles an hour.
No.
36 miles an hour. 46 miles an hour.
Huh?
50s.
Actually, 48 miles an hour.
Jeez.
Yeah, that was the average. So when he came out of the gate,
Cheetahs were the fastest, and they were like 30.
well, you can do the math. I'm just telling you that if you do a mile and a half in 1 minute 59 seconds, the math tells you that on average the horse is it was because at the start he's not traveling 48 miles an hour, so he had to accelerate.
Imagine being the jockey right
That'd be a thrill ride. And I was talking to a friend who bikes, and he was saying that going down a hill, typically the maximum speed he can get is 40 miles an hour.
Yeah.
Yeah.
I've been down like 20.
But he also doesn't have like giant.
Yeah, like you're riding on something that's going 50 miles an hour that's not motorized.
Yeah,
Yes.
on a straight curved path,
Yeah.
because you're going around those curves.
Riding
He forgot to put the 4 in the HF. Just leaving off one thing, it would cause him not to cross it out, and then he would show it up in his product, and then it would be wrong. So this is the really difficult part, is crossing these out, the ones that are the same, because you're not going to put them down in your final answer.
So the most difficult part of the problem is cross things out.
Yeah, making sure that your final answer is correct, because doubling it is pretty simple,
Yeah.
and flipping it. But then because you're looking, the eye is going over like 3 different lines or 2 different lines and then crossing out. So it's a complex skill, because you're not doing that on a daily basis.
Slowly, measuring the enthalpy to apply change as possible. Other reactions occur under conditions difficult to duplicate in a laboratory. Still, other produce products other than the desired ones. For these reactions, chemists use a theoretical way to determine delta H. Suppose you are studying.
You're always going to see a positive or negative delta H value, kilojoules. Elements in their standard states are delta H of 0. Did you hear why she said that? Because most of them aren't being formed on the Earth. Now, we can make them on the Earth, yes. There's some artificial elements like TC over there on the periodic table, technetium.
Have we found like another energy source like outside Earth?
We have fusion, we have fission, and those are the 2 nuclear things concerning elements. But the big problem is harnessing that energy, because right now you have to heat water, like a steam engine, and that's a lot of waste. With heating water, it takes a lot of energy to do that. So we'd rather just generate electricity. Like, I think it's Honda just came out with a hydrogen-powered car, and you just carry around the hydrogen gas. The military has them too. The military really likes them. You know why?
The military has everything first.
Why does the military like hydrogen-powered cars? Because you don't have to worry about a battery charging it. You can refuel it within like 4 minutes. It's got a 400-mile range, but there's another reason why I like it even more. Because it has a very small heat signal. It's super quiet too. I mean, you can just roll right up on them very fast, and they wouldn't even have a clue. Yeah, so the Special Forces units really like the hydrogen-powered automobiles. Now, they require a lot of precious metals. That is the ones the military is using, because they want them to be really,
So we're still ranking Africa.
well, they want platinum, typically.
Them as the sum of 2 or more simpler reactions. Hess's law. Sometimes it's impossible or impractical to measure the beta
Delta H?
Yeah, to measure delta H of a reaction by using a calorimeter. Consider the reaction figure 15-12. The conversion of carbon in its allotrophic form, diamond to carbon in its allotrophic form, graphite.
But that would be a pretty note to have there, that the standard state is at 25 degrees Celsius. So everything she's talking about here will be at that temperature. That is the values that they're coming up with for delta H. Now here, it says free elements in their standard state is assigned a 0 kilojoule. Why? Anybody know? Because elements typically are not formed on the Earth. They're formed in stars. Now we can do fusion and fission, but it's just not a standard environment. Most of the reactions that we deal with every day are going to be chemical reactions. So the elements are already here, so we're going to just consider them to be already formed. So that is elements. Whenever you see an element in your reaction, it's going to have a 0 value. Whole numbers like 1 and the reactants are fractions. The reason why that is, once again, is because we really only are concerned about the products. The products are how you make money. So if it's easier to manipulate them when you're trying to figure out your reaction, that is, if you have 4 that you need in your products that you're working on, you just multiply 1 times 4. So it just makes it a little easier to do the math if you already have the 1 in the product. Nice job with the notes, TT. Sierra, nice job.
Practice. So how do we do that? Well, we can employ Hess's law. Hess's law, don't forget, is
of the products, the delta H of the products minus the summation of the delta H of the reactants. Now, they have 2 ways to do this so they can double check themselves. It's kind of like with the Kentucky Derby. What's the length that the horses run? Anybody know?
1 mile.
What? No.
2 miles. 1,500 feet.
It used to be 1.5. The original Derby was a 1.5 mile, and they changed it in like 1896 to a 1.25 miles.
Do you know
right?
if they can afford horses?
No.
Because they can only go at their fastest speed for a quarter of a mile.
Well, who knows the horse that has the current record in that distance? Secretary, what was the time?
Real fast.
1 minute 59 seconds. So what rate of speed? Now, if you go on the ACT, you'll have to calculate questions like this. So what rate of speed is the horse traveling?
I don't know. Very, very fast. I'm doing that. Very fast.
Well, if you take the 59, you got to divide the 59 by 60 to get it into minutes. So it's around 1.98 minutes, right? So velocity equals distance divided by time, which would be hours. So you take the 1.25 divided by the you got to divide the 1.98 by 60. So it's around 0.03 hours. And then you're going to calculate that. It's around 37 miles per hour.
37?
Yeah. So she's traveling around 37 miles an hour. Or he is. Secretariat is. Always happening. Like the Kentucky Derby was changed. So you've got to be able to double check what you're doing to make sure you're right. They're constantly making new cars. Like the military, what is their what's the car that they prefer? Right now? They prefer the hydrogen car. Why? Because it has a lower heat thumbprint. You can go into a potential hazard and not make a lot of noise. H of 0 is equivalent to log of 1. So if the concentration is 1, you have 1 molar. So at a pH of 0, you have 1 mole of hydronium ions, H plus ions. Can you have a pH less than 0, Koenig? Can you have a pH less than 0?
No, you can't.
Yes, you can. Under extreme conditions, you typically don't, because 1 molar hydrogen ions, but you can have an 18 molar solution. You typically don't do a lot of like human biology in those conditions. 18 molar is just, it's going to dissolve your hand and kill all the bacteria. So you can have a pH lower than 0. Just be aware that when we are dealing with life, it's usually between 0 and what? 14. Because 7 is neutral, right?
To carbon in its allotropic form, graphite. This reaction occurs so slowly that measuring the enthalpy change is impossible. Other reactions occur under conditions difficult